This video is on arrays and pointers. First, let's talk about the relationship between arrays and pointers. The array name is the starting address or memory address of an array. So if I had an array called vowels, which is an integer array that contained 3 elements, 4, 7, and 11, each of those elements has its own unique memory address. And these memory addresses are going to be in consecutive order because arrays are in consecutive order in memory. So if integers are 4 bytes each on your machine, and the starting memory address of this array is 4A00, the next element would be 4A04, and the next one 4A08. And if I were to print out the name of the array, it's going to print out the starting memory address of the array, 4A00. If I were to print out the actual element of the array, the value, val sub 0, that's going to display 4. An array name can be used as a pointer constant. For example, given the same array that I had in the previous slide, if I did cout and then use the indirection operator before the name of the array, this is going to display 4. So we're dereferencing the array name, and the array name contains the memory address of that first element, which is why if you dereference it, it's going to print out the value of the first element. Also, you could create a pointer and make that pointer point to the array, and then you could use that pointer as an array name. So here's an example of that, pretending again that we have this array called vowels, and then I create a pointer which is allowed to point to an integer, and I set val pointer equal to vowels. Now notice I do not have to use the address operator here. That is because vowels already contains a memory address. So if I were to put a memory address here, it would say memory address of the memory address of the array, which would be wrong. So you just have to do a direct assignment here. And then I can use the name of the array in array notation, such as cout val pointer sub 1, and that's going to display 7 to the screen. Notice I said array notation a moment ago. There's also a different notation called pointer notation, and that's what I'm introducing you to in this module. Given the exact same array that I've already shown you, this vowels array, and that I have a val pointer, which is a pointer to an integer, and I assign val pointer to have the memory address of vowels, so that I can either use vowels or val pointer as my array name. Both will work. My question here is, what is val pointer plus 1? Okay, so val pointer is a pointer. It holds a memory address, right? So I'm getting my pen here. If this is a memory address, and let's say the memory address is 4A00 again. If I add 1 to that memory address, it's not going to make it 4A01. What it's actually going to do is it's going to add 1 times the size in bytes of an int, so 4 bytes. So it's going to add 4 bytes. So it's going to be 4A04. So when you add 1 to a pointer, you're adding you're going to the next memory address of the next element in the array. Basically, it's like putting the index of the array. So right here, this line right here, I have parentheses around val pointer plus 1. So we already know that this is 4A04. And this is assuming that this first element is 4A00, this one is 4A04, and this one is 4A08. So val pointer plus 1 is 4A04. In other words, it holds the memory address of the second element. So now if I use the indirection operator to dereference it, we're now talking about the value that this pointer points to. The value that this memory address points to would be 7. This is called pointer notation when you dereference a pointer that points to an array element. Let's look at the next one, val pointer plus 2. Well, if val pointer holds the memory address of the array 4A00 and we add 2 to it, it's really adding 2 times 4 bytes, which is 8 bytes. And that takes us to 4A08. Well, 4A08 is the third element in the array with index 2. So notice this number is always the index number. And then we're dereferencing it, so we're actually talking about the value that 4A08 points to, which is 11. Why do we have to have those parentheses? You have to use these parentheses right here and here because our indirection operator has higher precedence than our addition operator. And so pretending that we don't have the parentheses, what's going to happen is it will first dereference val pointer, which dereferencing val pointer would take us to the 4 in the array, and then it would add 2 to that value, so it would make that 6. Well, that's not what we're wanting to do here. We're actually wanting to access the third element in the array with index 2. You can use pointer notation or array notation interchangeably. One is not better than the other. Here are several different ways, so 4 ways that you can access array elements using either the array name or the pointer name. So remember, vals is our array name and val pointer is our pointer name. So one way, which is the way we've been using up to this point, is using the array name in subscript notation or array notation. The next example shows you using the pointer name in array notation. The next example shows you using the array name in pointer notation. And the last example shows you the pointer name in pointer notation. All 4 of these ways work perfectly and do the exact same thing. It will access the third element in the array. So just to be clear, array notation would be val sub I, and it's equivalent to pointer notation, which is star parenthesis vals plus I in parenthesis. Just like with array notation, pointer notation still does not have bounds checking. So it's possible to get out of bounds using pointer notation. All right, I have 5 examples that I'm going to show you with using arrays and pointers. Array pointer 1 has an array called numbers. It's a short array. And numbers is implicitly sized, so it has 5 elements, 10, 20, 30, 40, 50. I print out the first element of the array using the array name with the indirection operator, so it will dereference numbers. This is going to print out 10. Then the next line, I am saying numbers, which holds the memory address of the first element, plus 0, so it still holds the memory address of the first element, and then I dereference it. So basically lines 17 and 18 do the exact same thing. Then line 19 accesses array element 0 using array notation, and so this also does the exact same thing as 17 and 18. And then line 20 is the only line that's going to print out something different. It's going to print out the memory address of numbers. Now I'm going to add one more line here just to be to show you how this works. What if I say I want to print out the memory address of numbers sub 2? That's going to be this third element. Okay, a short takes up 2 bytes. So we should see that line 20 prints out a memory address that's 2 bytes before this memory address of number sub 2. Okay, let's take a look at this example. I need to open up my command prompt where these programs are. Then G++ array pointer underscore 1.cpp. So let's look at the code with the output side by side. So print out 10, 10, 10. That's because all 3 of these do the same thing. Then it print out the memory address of the first element of the numbers array, which is this big old long hexadecimal value that ends in 6. Then it prints out the memory address of number sub 2. So if you think about it, 6 going to A is 6 all the way through 10. That's 4 bytes. So we added 2 bytes 2 times in order to get to this. So 4 bytes makes sense. All right, let's look at array pointer 2. Array pointer 2 has a 5-element integer array named numbers. And then I ask the user to enter 5 numbers, have a for loop that allows me to read those values in. So normally this is how we write this, what I have highlighted on line 22, but I've commented that out because I wanted to show you pointer notation. And so here I use the indirection operator and then in parentheses numbers plus count. Then I have another for loop that just prints these numbers back out to the screen. So if I were to run this, it's going to show me, the user, entering in 5 numbers and then those 5 numbers printing back out to the screen. Okay, array pointer 3. Okay, I want to talk about this one a little more. We have a constant integer num coins, which is our size of our array. And then we create a double array called coins. And so coins is a 5-element double array. And it has a full initialization list. .05, 0.1, so that's 10 cents, right? 25 cents, 50 cents, $1. Okay, so there's our coins array. Then I also created on line 18 a pointer that's allowed to point to a double called double pointer. I also have a variable called count, which isn't initialized, so it's just junk data right now. Line 22, I place the memory address of coins in double pointer, which means that double pointer is also another name for coins. They both are the name of this array. Then in the for loop, I iterate through the array using a for loop, and I use the pointer name with array notation. So the first time I'm in this loop, I'm going to make this a little bit smaller and push it to the left. Okay, the first time I'm in this loop right here, I am count is 0, and 0 is less than 5, so it's going to print out double pointer sub 0. So it's going to print out 0.05. Then count is incremented to 1. And so then it's going to print out double pointer sub 1. which is going to be this second element. So notice that double pointer doesn't change what it's pointing to. It's always pointing to the beginning of the array. But with array notation, you can access other elements of the array through using that index. Now this next for loop, we have another loop that completely iterates through the array, and we start count back out at 0, and count is less than 5. And so the first time we're in this loop, it will be coins plus 0, so the memory address plus 0, and then we're dereferencing that. And so that's going to be this first element. Basically, it's going to print out this array all over again, but this time using the array name, but in pointer notation. This example is a little bit different. I just want you to be able to visualize it. I shouldn't erase that coins array. I forgot that it's in this one as well. Same array as the last example. 0.05, 0.10, our quarter, our 50-cent piece, our dollar piece. Okay, this time we have double pointer defined on line 18. We have count, so all of that's the same. What's different is my for loop. My for loop is going to iterate through the whole array, but on line 26, notice that I set the pointer equal to the memory address of coins sub 0. So that is going to make double pointer point here. And then I dereference double pointer. So this is going to print out 0.05. Then count will be incremented to 1. And then line 26, the memory address of coin sub 1 is going to be placed in double pointer. So in this example, we actually are changing what double pointer is pointing to at each iteration of the array, and then dereferencing that pointer. So it works just a little bit different. One last example. I have a different array this time, a 4-element array called set. That should be a 3. So those are my index values. And then set is initialized, so we have 5, 10, 15, 20. Then I also have a pointer variable called numPointer. On line 20, I make numPointer point to set. And then on line 23, it prints out the numbers in set are, and we have a loop that will iterate through the array, and it's first going to print out or a dereferenced numPointer. So it's going to print out the value that numPointer is pointing to. So I'm going to write out what's going to be printed here. It's going to print out 5 first, because that is what numPointer, the value numPointer is pointing to. Then look here, line 27, we're going to increment numPointer. Okay, so pointers, remember I talked about how adding 1 will add not just 1, but 1 times the number of bytes in that data type. Same thing here, we're only adding 1, which is going to add, if set is an integer, it's going to add 4 bytes to the memory address that's stored in numPointer. Basically, this is going to make numPointer point to the very next element, like that. Then count is less than size, so we get back in the loop, and it's going to print out a dereferenced numPointer. It's going to print out the value numPointer is pointing to. So that's 10. Then it's going to increment numPointer, which is going to make numPointer point to the next element, then dereference it, so 15. Then we'll get in the loop again, and then we increment numPointer, right? Increment num pointer, count is still less than size. We will print out the dereference num pointer, which is 20. And then num pointer increment. So this is the part that might be confusing at first, because what happens is num pointer is going to point to the element that's just out of bounds of the array. But this ends up being okay, because down in the next loop, look what we do at the very beginning of the loop. So this loop, its purpose is to print out the numbers backwards. So the very first thing it's going to do is decrement num pointer, which is going to make num pointer point to the element at index 3. Then print out the dereference num pointer, so print out 20. Then we decrement num pointer again. And then dereference num pointer, so it's going to print out 15. Decrement num pointer again. Dereference num pointer, so it's going to print out 10. Decrement num pointer again. And then dereference num pointer again, which will print out 5. And at this point, count will not be less than size, and so we will not get in this loop again. Okay, I'm just going to show you that this is how this program behaves. This is the only one I'm going to run. G++ array pointer underscore 5.cpp. The numbers in the set are 5, 10, 15, 20. The numbers in the set backward are 20, 15, 10, 5.